Hello everyone, welcome back to Algebra 1 with Miss Betsy. I sure hope that y'all enjoyed your Christmas time and that rare snowfall that we had on Christmas Day. We had about 4 inches out at my house. It was just gorgeous watching it. So I know that we're not back in school yet and you're probably not really particularly excited the thought of getting going with algebra, but you know what? We're going to go ahead and start anyway. Before we get started though, you know I've got a lame joke for you. And this is from an ancient riddle book, library discard. These were the types of riddle books that I used way back in the dark ages when I was your age. Actually, when I was younger than you. Question: why does a stork stand on one leg? Well, a stork stands on one leg because if he stood on no legs, he would fall down. The next one. Name 5 things that have milk in them. Well, those 5 things would be butter, cheese, ice cream, and 2 cows. So, there's your lame jokes for today. We're going to go ahead and continue with our study of relations, functions, and graphs. For those of you who are using the same text that I am using Algebra 1 for Christian Schools by Bob Jones University Press. I have the 2nd edition, and today we're in section 6.2. We're talking about relations and functions, and we are on page 223. And so that this thing doesn't drag on, so that I have it smaller rather than letting this lecture drag on forever, I'm going to be referring to the book a whole lot more frequently than I do, because I want to make sure that I touch on everything that's in here, but it's somewhat long and tedious, so just sort of bear with me on this one, okay? First, we want to talk about what a relation is. And a relation in mathematical terms has a specific meaning, and a relation is any association. Oh my, it's been a while since I have written on the board. Plus it's cold. Any association between 2 or more things, and specifically it is referring to any set of ordered pairs. And when we first come up with the idea of a relation, something that's a very common example of this would be the relationship between prices and items or objects that are available for purchase in a grocery store. And we could sort of set ourselves a little chart here that illustrates that relationship. And we could say that in the X category, we have some prices here. Well, I'm going to say 88 cents and 93 cents. And in the Y category, we're going to have apple, gum, and a candy bar. When we were going over this in class the other day, the day before we got out for Christmas break, the kids were saying, well, do you see exactly what I did? I was going to say candy bar. I was going to tell you about what we did in class, and the kids said we had monsters. So I wrote down a candy monster. So we'll just go ahead and say candy. And the way that you read this chart is you see that for 79 cents you get an apple. For 88 cents you get gum. For 93 cents you can buy a candy bar. So what this illustrates to us is that there is a relationship that exists between 2 items. And that's all that a relation is. It's just a set of ordered pairs. And we can go ahead and illustrate what we're talking about here with ordered pairs. Now remember that ordered pairs took the form x, y. This is an ordered pair, and it's called an ordered pair because the order in which those two numbers show up in there is important. you can graph these points on a Cartesian coordinate system, and first you graph where the location of the x value, then you graph the location of the y value, and if you switch those around you get two different locations. So a relation is a set of any set of ordered pairs. So what we're going to do now as we go ahead and move over to page 224 in our text is we're going to show that there are basically three different ways that you can indicate relations. First off, we said that a relation was a set of ordered pairs. So we're going to first off make sure that I can see that. We're going to use a set, so we have to use our set builder notation. Those braces, a set of these ordered pairs indicated by -3, 5, 2, 2, 2, 4, and 4, -1. 2, 4, and 4, -1. This is one of the ways that we can indicate a relation. We indicate it as a set using set builder notation of ordered pairs. These ordered pairs represent three locations on a plane, which four, 1, 2, 3, 4 locations on a plane, which I'll show you in just a minute. A second way that we can identify this same relation, or this same set of four ordered pairs, is by using a chart where we have an x and a y, our -3, and our y is 5, x is 2, y is 2, x is 2, y is 4, x is 4, and y is a -1. So we have set notation, we have chart where what value do we have? If x is -3, y has to be 5. If x is 2, y has to be 2. Or if x is 2, y can be 4 here. If x is 4, y is -1. And someone in class said, oh, but this is not a function, but it's a relation. Exactly true. We'll talk about functions in a moment. But this describes a relation. And another way that you can show a relation is to actually show this graphically by plotting all of these points on a Cartesian coordinate system. And I'm just going to show you a portion of that Cartesian coordinate system. Now usually when you've seen me draw graphs before, I sort of make the x and the y-axis the same length. Do I need to do that? No, it's perfectly fine for me to draw it like this where you have shorter legs, because that arrowhead on the end, it illustrates to you, signifies to you that this line continues infinitely to the positive and negative direction on the x-axis. It also continues on infinitely in the positive direction for the y, the negative direction for the x-axis. So now let me go ahead and 1, 2, 3, 4. 1, 2, 3. -3, -2, -1. I'm just sketching in locations on my graph. For the y, I need to have 1, 2, 3, 4, and 5. 1, 2, 3, 4, 5, and for the x, I'm just negative. For the negative y's, I'm just going to put a -1 and a -2. As you're sketching points, as you're plotting points, sketching graphs later in this section, you don't have to have symmetry with how you label your graph. The scale has to be the same. I'm going up by 1, 2, 3, 4, 5. But here I have a +5, a -2, and that's all right. You don't have to go +5, -5, +4, -4. Now the third way that we're going to indicate or define or illustrate this relation here is by actually going in and plotting these 4 points on our Cartesian coordinate system. So if we have a negative 3, 5, we're going to go first to the negative 3 on the x-axis, and we're going to count up 5 units. 1, 2, 3, 4, 5. So put our dot here, and this is the location of the ordered pair negative 3, 5. It's at the intersection, roughly, since I'm just sketching, of negative 3 and 5 on our coordinate system. Then I have, if x is 2, y is 2. And then I also have, if x is 2, y is 4. So I'm going to have x is 2, y is 4. The location of my 4th point, the 4th ordered pair here, is x is 4 and y is negative 1. And I'm looking at this, and I'm no more interested in being back in school really than you are. I just graphed 3, 2 and 3, 4. So let me go ahead and correct my error there. X is 2, y is 2, x is 2, y is 4. That's why we really like to be able to erase things. The final point that I want to plot, x is 4, y is a negative 1. So what we have here is 3 different ways to define the same relation. You can just list all of the ordered pairs in a set, you can show them on a chart, you can actually plot them on a Cartesian coordinate system. Now, the set of all of the x-coordinates is called the domain, and the set of all the y-coordinates is called the range. Okay, I'm going to go ahead and move back here. The domain, you can still see me. This is the set of all the set of all x coordinates. So what would be all of the x's that we have? And if we want to use set builder notation, the x's would be negative 3, 2, and 4. And you say, but Miss Betsy, 2 is used twice. That's right, because there are 4 points that are included in this relation, but when you're showing the domain, you do not repeat the numbers. So to indicate the set of all of the x-coordinates here, it's just negative 3, 2, and 4. The next word that we're going to talk about is range. Next word we're going to define here, and if the domain is the set of all of the x-coordinates, what do you think the range is? That's exactly right. The range is the set of all y-coordinates. Now, what are our y-coordinates? Just write them. And go ahead and write these numbers always when you're in a set. Write them in ascending or increasing numerical order. So the smallest y is going to be negative 1, 2, 4, and 5. So these 3 elements represent the domain. These 4 elements represent the range. So this is the domain, and we're going to indicate that with a capital D. This right here is the range, which we indicate with a capital R. Now, I'm going to go ahead and erase these 3 different ways of illustrating this relation, because really all we're interested in right now is the domain and the range of this function. And I'm going to go ahead and transfer my information over here. The domain is negative 3, 2, 4, but it's the set that contains those 3 elements, so you have to use those braces. And the range is a set that contains the elements -1, 2, 4, and 5. And we're not ever going to write down range and domain anymore unless we're literally writing out a definition. And you'll know automatically, you see the capital D, it's the domain, which is all of the x values. You see the capital R, it's the range, which is all of the y values of a relationship. And you know that the x, when you have x and y values, what you have defined, or what you have described there, are ordered pairs. Now, there's a way that you can illustrate the relationship, those ordered pairs, when all you have is the domain and the range. And these are circle graphs. First, you're going to have the domain in the first circle. You're going to have the range in the second circle. So in our domain, we have -3, 2, and 4. And in our range, we have -1, 2, 4, and 5. We're going to label those always domain and range, but when you draw these circle plots here, the domain always is first. And on the right, to the right of the domain, we're going to show the range. So, what are we going to do? We're just going to draw arrows saying which goes to which. -3, according to our original problem, which I erased for you, but you can see this on 224. Our first ordered pair was -3, 5. Our second ordered pair was 2, 2. Our third ordered pair was 2, 4. And our final ordered pair was 4, -1. And does that look a little bit messy? Yeah, it does. But there is no way to draw it neater. I mean, you can draw it more neatly when you have the fine pencil line than I can with a marker, but it's just not real particularly neat. So now let's review. What is it that a domain is? The domain, according to your book, is the set of first coordinates of the ordered pairs of a relation. So what was our relation? We had a specific relation that was defined to be the set containing the ordered pairs -3, 5, 2, 2, 2, 4, and finally, the last ordered pair was 4, 1. So we have this relation, consists of these 4 ordered pairs. The domain is the set of all of the first coordinates. The range is the set of all of the second coordinates. So your domain is your x values, the range is your y values. And I've tried to come up with some sort of a thing that helps you remember, like dx and ry. I don't have a memory aid to help you. You just have to memorize the domain is all of the x's, the range is all of the y's. Okay? So now, I think I have a well-used teacher manual here. Moving on to page 225. Now, a little bit ago I said, some of you will realize and will be noticing, hey Miss Betsy, this is a relation but it's not a function. And I said we would talk about functions soon. We're talking about functions now. And what a function is, it's a very special type of relation. So let me go ahead and draw a picture here. Just a little graphical picture. You have all this big old group of relations, a big old set of ordered pairs. And inside that, so this is a relation, and here's a function. Functions, what this says is all functions are relations, but not all relations are functions. Okay? A function is a specific, smaller piece, smaller grouping of ordered pairs. And what a function is it can't have... Did you hear that noise? That was just snow falling off my roof and crashing on my porch. A function cannot have two or more ordered pairs with the same first coordinate. Every first element is paired with a unique second element. Unique means one and only, the only one of its kind. Now, you can't not pick up the easy illustration here, since we're teaching from a Christian text, that Jesus is the one and only. He is unique. Okay, there's one and only Savior, one and only Jesus. Okay, functions for each x, there is one and only one y that can be paired with that. And you need to be able to write this down for me. So, I'm going to write out the specific definition I want. A function, this is a relation in which each x coordinate is paired with one and is paired. Too bad I can't write as fast as I can speak. Is paired with one and only one y coordinate. This is the definition of a function. A function is a relation. A relation is a set of ordered pairs. So a function is a relation in which each x-coordinate is paired with one and only one y-coordinate. So what I've said before earlier is all functions are relations because they're a set of ordered pairs. But not all relations are functions. And that relation that we mapped out just a little bit ago in this illustration, in this lecture, was not a function. So, see, we're looking at example 2 now on page 225. It says the Cartesian graph and the circle model are two different representations of the same function. Is the relation a function? Okay, so what we have a picture of is this graph. And we have one, two, three, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9, 8, 7, 6, 5, 4, 3, 2, 1. We have 3 points that are plotted here. We have the first point is 1, 9. The second point is identified by the ordered pair 2, 8. The third and final point is labeled 3, 7. So this, we said we have two ways to represent the same function. We have our Cartesian graph. The points are plotted on a Cartesian coordinate system. And we have a circle model. So how are we going to do our circle model? Well, the first circle is the domain, which is all of the first coordinates, or all of the x values. 1, 2, 3. Our range is all of the y values. 7, 8, 9. And our circle plot, circle map, says that if x is 1, y is 9. If x is 2, y is 8. If x is 3, y is 7. Now what's the question? The question is this relation, remember a relation is a set of ordered pairs, does this relation describe a function? And yes, because each element of the domain is paired with a unique element in the range. In other words, every time there's an x, there's only one y that goes along with it. When you are a husband, you have only one wife. When you're a wife, you have only one husband. It's an example of a function. For every x, there's one and only one y. So therefore, this relation, this set of three ordered pairs, is a function. So now let's go ahead and look at back to what our original relation was that I told you wasn't a function and that some of you figured out. Here was our original relation. We had the ordered pairs -3, 5, 2, 2, 2, 4, and 4, -1. We know it's a relation because it's a set of ordered pairs. There are 4 ordered pairs in there. Why is it not a relation? Why is it not a function? Because of these 2 ordered pairs in the middle. Remember, for it to be a function, each x has to be paired with one and only one y. -3, 2, 4, -1, 2, 4, and 5. We have 3 pairs with 5, 4 pairs with -1. All right so far, isn't it? But we've got this problem here. Our x has 2 partners. If x is 2, y can be either 2 or a 4. That violates the definition of a function, which says that for every x, there has to be one and only one y. So therefore, this relation here, even though it's a relationship, yes, because it's a set of ordered pairs. It's a relation. It is not a function because the x has more than one y associated with it. This is the key important definition, distinction between a relation and a function. And they have a really neat little trick that you can use to just look at the picture of a graph and say, oh yes, it's a function. No, it's not a function. It's what they call the vertical line test. Let me go ahead and show you this. We have this relation that we're plotting here on our Cartesian coordinate system, 1, 2, 3. We have this, we have this, we have this point, we have this point. 1, 2, 3, 1, 2, 3. Make sure when you're doing your graphs, you take the time to use a straight edge, grid paper, label your graph completely, label your ordered pairs. This is the point 1, 1, this is the point 1, 3, this is the point 2, 2, and the point identified by the ordered pair, 3, 3. So is this a function? Why or why not? Exactly. Right here we have 2 ordered pairs that have the same x value. And you know what our secret is, what our trick is? They have something called the vertical line test. Take your straight edge and run this through, run it up against your graph. If more than one point hits that straight edge, it's not a function. We say that it fails the vertical line test. So if you can draw a legitimate vertical line through any 2 points, then it means that it is not a function. So this here fails the vertical line test, so it's not a function. How else can you tell it's not a function? Well, you could draw yourself a circle graph. What are our x's? 1, 2, 3. What are our y's? 1, 2, 3. How do these pair up? If x is 1, y is 3. If x is, whoops, right there. I drew it the wrong place. But we have two pairings with our x guy being 1. It can be 3 or 1. And that violates the definition of a function. For every x, there can be only one y. Every husband, only one wife. We've got a husband here, 2 wives, not a function. Got an x here, 2 y values, not a function. Okay? You can show it with a circle graph, but this vertical line test here is just fast and easy. That's the end of section 6.2. I'll see you next time.